Imagine trying to remember, I don't know, every single detail from some huge multi-volume book series instantly,
Yeah,
perfectly.
like Dune or
Like
something.
exactly. And then having to answer questions about it, not just one book, but like a whole library every time you step inside.
That's actually a pretty good way to put it. That's kind of the challenge large language models face with really long information. It's been this massive hurdle.
Okay, so let's unpack this then. Today, we're doing a deep dive into some really fascinating new research. The paper's called Atlas, Learning to Optimally Memorize the Context at Test Time.
Right. It's by Ali Baruz and some colleagues over at Google Research.
And it's all about pushing those boundaries, right? How AI models handle these huge amounts of info, basically giving AI a much better memory.
Exactly.
Yeah.
And what's interesting is that transformers, the powerhouses behind most models today, they're amazing at certain things, like finding info you just gave them that's in context retrieval.
Right.
But they really hit a wall when that context gets super long.
Why is that, though? What's the actual bottleneck?
It's this thing called quadratic complexity. Um, Basically, the memory space and the processing time they need just balloons, like exponentially as you feed them more info,
Ouch. So it gets slow and expensive fast.
very fast. It's like trying to remember a super long phone number, and for every extra digit, the effort somehow triples. It just doesn't scale well.
So, if transformers have this scaling problem, what about other methods? Did people try different architectures?
Oh, absolutely. People have tried things like modern RNNs, recurrent neural networks. They try to be more efficient with memory.
Did they work better for long stuff?
Well, they often struggle in other ways.
Yeah.
Their memory might just be too small, or they kind of only learn from the very last thing they saw.
Like having a really short attention span?
Sort of, yeah.
Yeah.
Their memory management isn't always, let's say, expressive enough to grasp the whole big picture in really deep contexts.
Okay, so every AI breakthrough seems to start by finding one of these bottlenecks. And for LLMs, memory, especially with tons of information, is clearly a big one. So, what did these researchers, the Atlas team, see as the fundamental flaw they really needed to fix? Our mission today is to explore how they're tackling these limits. We want to give you a shortcut to understanding how AI might get much better at deep, long context understanding.
Well, the flaw they really zeroed in on is how most existing AI memory models work. They tend to treat memory almost like a list of separate events,
Okay.
and they optimize what they remember based only on the immediate current piece of information they're processing.
Ah, so it's like trying to follow a whole conversation just by remembering the very last word someone said.
Exactly that. It's this online nature, as they call it. It means the model often misses the bigger picture, the full context of the document or the dialogue.
Right. You lose the forest for the trees. So if that's the problem, this sort of reactive, short-sighted memory, what's their fix? What's the big idea they came up with?
Their core idea is this concept called test time memorization.
Test time memorization.
Okay.
What does that mean? Is it about learning during testing?
Not quite like learning new skills permanently, the way models do during training. It's more about how the model stores and retrieves information specifically within the context it's currently working on, right when it needs it.
Okay, so like when I quickly scan a long email to find that one specific detail I need right now for a reply.
Precisely. The model needs to do that efficiently at test time. It's not just about cramming more data in during training. It's about changing how the AI's memory works in the moment to build a more coherent understanding of long-form text.
So it can reason over the whole thing, not just bits and pieces.
Exactly. It's a shift from reactive memory to building a robust model of the context.
And that leads us to their actual solutions, right? Atlas and you mentioned OmegaNet.
Yes. These models are designed differently. They learn to memorize a window of context.
A window.
Yeah, not just isolated data points. So think less about remembering the last word and more like remembering the last paragraph or maybe even the last page you just read.
Okay, that sounds much more useful. How do they actually do that? How do they memorize a whole window?
They use a new rule for updating the memory. It's called the Omega Rule.
Okay, Omega rule. Different from the old way.
Very different. Most older models use something like a Delta Rule that typically just adjusts memory based on the very last input.
The forest for the trees problem again.
Right. The Omega Rule, instead, optimizes the memory based on all the recent past tokens within a specific, defined sliding window.
Ah, so it looks back over a chunk of recent history, not just the last millisecond.
Exactly. And that makes it strictly more powerful because it's considering that broader context when it decides what and how to remember. It's like updating your notes based on the whole meeting segment, not just the last sentence someone uttered.
Okay, that makes intuitive sense. So building on that,
Yeah.
how do they actually expand the capacity? You said earlier models had limited shelf space. How do Atlas and OmegaNet get more shelves or make the shelves hold more?
Right. Capacity is key. They use something called higher order feature mappings, specifically polynomial kernels on the input tokens.
Polynomial kernels. Sounds technical. What's the effect?
The effect is that it dramatically boosts the number of unique key value pairs the memory can perfectly store and recall.
Okay, so back to your library analogy.
It's like making each shelf in our library able to hold exponentially more complex or intertwined books, not just simple, separate ones.
So the model can genuinely remember more distinct facts or ideas without getting them jumbled up.
Precisely. And connecting this to the bigger picture, it also provides a theoretical reason why deeper memory models with more layers in their memory part actually increase capacity. More layers, more information storage potential.
That sounds like a fundamental improvement.
It is. It's about improving how much a memory unit can actually encode.
Okay, so we have bigger shelves, or more complex shelves, but you still need a good system to manage them, right? Like a librarian. You mentioned most models use basic gradient descent, which can get stuck.
Yeah, basic gradient descent is like, well, it finds a way down the hill, but maybe not to the very bottom. It can get stuck in less than ideal solutions, especially with complex, long contexts, like a librarian who always takes the same route, even if it's inefficient.
So what's Atlas's smarter librarian?
Atlas uses something called the muon optimizer.
Muon, like the particle.
Maybe. But here, it's an optimizer, and it's smarter because it approximates second-order information.
Second order, what does that mean practically?
Practically, it means the optimizer doesn't just know which direction to adjust the memory contents, but it also has a much better sense of how much and how fast to adjust them for that specific situation.
Ah, so it's more adaptive.
Highly adaptive. It helps the memory converge to genuinely better storage solutions, especially when dealing with really long streams of information. It leads to what they call locally optimal memorization.
Which means more effective, more reliable recall in the end.
Exactly. Think of it like a librarian who doesn't just know where to shelve a book, but instinctively finds the perfect spot so it can be retrieved instantly, even if thousands of new books suddenly arrive.
That's a powerful idea. So this isn't just tweaking existing models then. You mentioned this work actually generalizes the original transformer architecture itself.
Yeah, that's one of the really fascinating parts. Their Omega rule and this whole concept of deep, well-managed memory can be seen as a generalization of how transformers work.
How so?
Well, remember those polynomial kernels we talked about for boosting capacity?
Yeah.
They offer a big boost. But the original transformer uses something slightly different, an exponential kernel. You can think of this kernel mathematically like a polynomial with infinite terms using a Taylor series approximation.
Infinite terms,
Yeah.
so infinite capacity, theoretically.
It maps the inputs into what's effectively an infinite dimension. That's a key reason why transformers, in theory, have such potentially unbounded memory.
Okay, so how do the researchers use this insight?
They created something called deep transformers. They basically took their deep linear attention model, which used the polynomial kernel, and swapped that out for this more powerful, infinite dimensional exponential kernel from the original transformer. But they kept their concept of deep memory layers.
So combining the transformer's powerful kernel with their improved deep memory structure.
Exactly. Best of both worlds. And then they took it one step further with DOT.
DOT.
DOT stands for Deep Omega Transformer. This integrates their Omega rule into the deep transformer architecture.
Ah, so DOT gets the powerful kernel, the deep memory, and the smart Omega rule updating.
You got it. This means DOT doesn't just append new information like a standard transformer. It intelligently updates its memory based on predicted values from its previous state. It's much more dynamic and context-aware.
Wow, okay. That sounds complex, but potentially very powerful. Did it actually work? What did the results show?
Oh yeah, the proof is definitely in the pudding, as they say. The experiments really back this up. Across a whole range of different tests, language modeling, common sense reasoning, and particularly tasks involving really long contexts, Atlas, OmegaNet, Deep Transformers, and DOT just consistently outperformed the older transformer models and also more recent linear RNNs.
It's not just a little bit better?
No, significantly better in many cases. A real leap, especially in the long context stuff.
Okay, give me an example. What's a
Yeah.
really striking result?
All right, check this out. There's a benchmark called Babylon. It's specifically designed to test models on ultra-large sequences, like
Oh.
really punishingly long.
Okay.
On that benchmark, Atlas not only maintained its performance as the sequences got incredibly long, but it achieved plus 80% accuracy at a length of 10 million tokens.
Wait, plus 80% compared to what?
Compared to its own baseline at shorter sequences, showing it didn't degrade. And critically, at that 10 million token length,
Yeah.
other leading long context models, like one called Titans, saw really significant drops in their performance. They just couldn't handle that scale effectively.
Wow. 10 million tokens is enormous. That really shows the power of their memory management, the Muon optimizer maybe.
Absolutely. It highlights the combined power of the Muon optimizer, the polynomial kernels for capacity, and that core idea of memorizing the context with the omega rule.
Okay, what about other tests? Like finding specific information?
Yeah, the needle and haystack tasks.
Hmm.
This is where the model has to find one tiny specific piece of info buried in a massive document.
Like finding one name in a 1,000-page report.
Exactly. And Atlas and Deep Transformers did great there too. They even performed well on context 4 times longer than any they'd seen during training. That's strong generalization.
Impressive. Any tests focus purely on memorization itself?
Yep, there's a benchmark called May Memorizing Associative Data Loader. It specifically tests raw memorization ability. Atlas came out on top there too. Just clearly demonstrated a superior ability to retain and recall information accurately.
So it seems like while the original Transformers might still be really good at that basic in-context recall for shorter things,
They are, yes. They're still kings in certain scenarios.
but Atlas and OmegaNet and maybe Dot are seriously closing the gap and maybe even pulling ahead when things get really long or complex.
That's exactly the picture the results paint. These new approaches are highly competitive, and on these challenging long context benchmarks, they're often proving superior.
And it's not just one single trick they're using.
No, definitely not. They did ablation studies. That's where you systematically take parts of the model away to see what happens.
Right, to see which bits are actually important.
Exactly. And those studies confirmed that pretty much every component they introduced contributes significantly. The gated MLP memory structure, the hybrid architectures they tried MAG and MML, which mix attention types to polynomial mappings for capacity, and especially that Muon optimizer for management.
So it's the whole package working together.
It really is. All those pieces play crucial roles. Oh, and another important point, they found that these complex models can still be trained efficiently using parallel processing.
So they're not just powerful, they're actually practical to build and train.
Which is vital, right?
Yeah.
Doesn't matter how good a model is theoretically if you can't actually train it in a reasonable amount of time.
Absolutely. Okay, so let's pull back a bit. What's the big takeaway here? What does this all mean for AI?
Well, I think it means we've seen how models like Atlas, OmegaNet, and these deep transformers are genuinely tackling some of the biggest, longest-standing challenges in AI memory.
Things like the limited capacity, the sort of online-only updates that miss context, and the basic memory management.
Exactly. By bringing in these new ideas, the Omega rule for context-aware learning, the superlinear memory capacity from polynomial kernels, the smarter Muon optimizer, these models are showing they can understand and manage truly huge amounts of information, much better than before.
It feels like a new frontier, really, in how AI can remember and reason over these long contexts.
I think it is, which
Yeah.
leads to some interesting thoughts, right? Consider for a moment, as AI models get these increasingly sophisticated long-term memory capabilities, what kinds of tasks, maybe ones we thought were impossible for AI before, might they unlock for us? And maybe even more profoundly, how will our own interactions change with systems that are this highly informed, that can genuinely recall and use vast amounts of information, almost like we do?